This slot is shared by two speakers. The first speaker is Mr. Miyano, Tatsuya Miyano from Toyota Central Research and Development Labs. And the second speaker is Mr. Takemitsu Mori from Toyota Motor Corporation. So we cannot have Q&A session. Instead, they will stay here during the coffee break. So please ask them. Okay, please start.
Thank you very much for the introduction. Hello, everyone. My name is Tatsuya Miyano from Toyota. So in the first half of this slot, let me introduce our collaborative research with Professor Lombard from Georgia Tech and Professor Egerstedt from UCI. The title is Collective Unknown Object Transport by Non-Communicating Multiple Robot and a Human Participant. Okay, let me start. Okay, so before diving into the technical discussion, let me introduce our motivating examples. First, could you see the left figure? This is the picture of the Gion Matsuri Festival in Kyoto here. So in the parade of this festival, human participants collectively transport this cart along the road. So this is what we'd like to achieve in this research. Meanwhile, it is known that even a team of ants can achieve this kind of task. So, so how can I say the information processing capabilities of humans and ants are totally different. However, both of them can achieve this task. So from this observation, we can guess that this task does not require rich information. So we address this question. So what transporting capabilities can a group of agents have using a minimal set of prior information or communication? So this is an academic motivation. So we also have a practical motivation. So teams of autonomous robots are expected to significantly increase productivity. So they could play a key role to help human participants in the factory and logistics systems. So based on our minimalist perspective, we would discuss a possible human multi-robot collaboration on collective object transport systems. Okay, so in accordance with this trend, there are many research on the collective object transport systems. However, they apply centralized offline approaches or controller that does not guarantee optimality in terms of energy time efficiency. So in addition, there are potential issues on collective object transport systems. The first one is computational load because real-time actuation is required. The other one is communication failures that might cause unstable behavior of the overall system. The final one is that parameters of the object are unknown in practice. So to address these issues, we presented how can I say the solution for the force optimization problem. Okay, so in our framework, so we consider multiple agent and one object. So in the framework, each agent implement only the completely distributed PIVLC controller, which minimizes the control energy in steady state. So because the object mediate information implicitly between agent, so no communication between agent is necessary. Okay, so this is an experimental result. So 3 agents collectively transport this GT-shaped object through the S-shaped path. So diamond represent the tentative waypoint. This waypoint generated on the next corner of the path. So, so this is just a completely distributed PI/VLC controller. Just switching the local reference velocity, how can I say, reference target, they can pass the this S-shaped path, S-shaped route. Okay, so right, so let me introduce details of our approach. So let me start with formulating the object dynamics. For simplicity, we consider two-dimension case, but we can straightforwardly extend our solution for to the 3 dimensions. So we consider the single object and multiple agent. They are rigidly attached to the object. So here, V is the input matrix of robot. D is the input matrix of external actor, for example, a human participant. And f of x is a centrifugal force. So Ri is the cross product of agent i's position relative to the center of mass of object. So x is the linear angular velocities of the object. So U is the concatenation of input forces, and U sub ext is the external force. So we have this state space representation, and we have this system sigma sub x, where the how can I say, the relationship between the local velocity and the global velocities are given as this bottom equation. So we see that this relationship is very suitable for primordial framework that I will show you in the next slide. So we here consider this type of collective object transport problem where the objective function is the steady state energy input. The constraint is the velocity tracking constraint. So this type of problem can be solved by using this primordial dynamics. So the architecture of this primordial framework is as shown here. So in the primer update, which is equal to the distributed PI/VLC controller, so meanwhile, their update is equal to the object dynamics with a human participant. That is, the object manages the equality constraint that is the velocity tracking constraint through its physical dynamics. So this is a benefit of the primordial framework. Okay, so from this property, so we see that each agent does not need to care who a human participant is, because what each agent needs to care is its linear velocity. So this is, I think this is a very benefit of the primordial framework. So we here analyze the overall system based on passivity. Passivity is an input-output relationship against input-output property of the system, such that stored energy is less than the supplied energy. So here the object dynamics is shown to be locally passivity short. That is, under this locality conditions, this system is passivity short. So that is, the storage function of T is less than or equal to the supplied energy plus positive energy. So because this system has a positive energy, this is the passivity short system. On the other hand, PI/VLC controller is shown to be the strictly passive. That is, the derivative of storage function is equal to the supplied energy minus negative plus negative energy. So from this fact, we see that if this positive energy can be canceled by that negative energy, the overall system can be stabilized. So this is a discussion with the human participant. We consider with the case of human participant. So then we have this result. If the external force, this is the influence of a human participant, is constant, the optimality of input forces can be guaranteed. On the other hand, if the external force is passivity short, then the input converges to the suboptimal solution. So the convergence is guaranteed, but the optimality is not always guaranteed. Okay, in conclusion, so we presented a primordial framework for collective object transport systems, which amount to implementing a completely distributed PIBSC controller. So based on this minimalist perspective, we discuss a possible human multi-robot system where robots do not need to care who a human participant is, and passivity short human participants are acceptable. So in future work, we'll try the experimental verification of the human multi-robot system. Okay, thank you very much.
Okay, I'm Takemitsu Mori of Toyota. Thank you for inviting me this workshop. Honestly, my presentation is not about the academic content. My presentation is about the real-world trial. So I would be happy if you have interested in my presentation. So my title is Toyota's research activities on real-world applications. We were focused on the social issues solving the shortage of the workers due to the decline in the birth rate or aging population. And improving quality of life is also important issues for us. We believe that a mobile manipulator could be a solution to these social issues. And our ultimate goal is realize a robot that supports human daily lives, including independent living support, remote care support, housework support. The realization of mobile manipulator is very highly challenging, and we need to develop a various field of technologies. To this end, we continue research while setting milestones. We developed a prototype human support robot 2012, and we started a HSR developers community in 2015. I explain later. And last year, we developed HSR simulators to available as a OSS. At the same time, with continuous research, we think that it is necessary to apply the technologies achieved at each stage to the real-world applications. First of all, let me introduce our continuous research activities. We have developed a human support robot, HSR, as shown in this video. It is designed to be used in the house and it is capable of picking up and carrying object. And it's a small size and a simple mechanism with single arm. We are implementing the various technologies to this research platform and to realize our ultimate goal. But we think that it is very difficult to realize such kind of robot for a single company. That's why we established the HSR developers community to provide HSR to the researchers who share our objectives and to accelerate the research of mobile manipulator by sharing the research results and the knowledges. Currently, in the HSR developers community, 44 research centers from the 11 countries participate in. And the HSR developers meeting are held regularly to share the result of the research and their knowledges. Next, I will explain the real-world applications. In the past, we have adapted the technology to the parts transfer robot in our automobile factory. And now we are working on a hospital transfer robot at the Toyota Memorial Hospital to transfer medicine within the hospital. We are planning to operate multiple robots simultaneously to transport our medicine, and we plan to start full-scale operation in the next year. In this presentation, we will introduce the robot service at the Tokyo Paralympics game as another example of the real-world applications. Tokyo 2020 Olympics and Paralympics Games was held last summer after 1 year postponement due to the pandemic. The Tokyo 2020 vision is as follows: achieving the personal best, unity in diversity, connected to tomorrow. And the Tokyo 2020 was held within the aim of bringing globally positive reforms as the most innovative in history. To contribute to this vision, we had developed a stress-free entry and spectators support service for wheelchair users by using HSR. This robot service has two features. One feature is that the robot service is realized by combining the autonomous operation with the remote manual operations. And the service is provided by the remote operator who interact with the spectators through the HSR head displays, giving instruction for autonomous operation and operating the arm and the mobile base. Second feature is that remote operator teams was composed of a mixed teams of a person with disabilities and a person with non-disabilities. By utilizing this robot, people who have difficulties in going to the stadium will be able to provide the heartfelt services. We believe that promoting this kind of service would lead to the realization of the Tokyo 2020 vision. Now, I would like to explain the robot service in detail. First, leading to the seat service. A remote operator meets the spectator at the entrance and have the welcome conversation first. After that, the robot leads the spectator to their seat. This movement to the seat is autonomous, and it has a function that when the spectator leaves a certain distance, the robot will stop. When arriving near the seat, it switches to the remote control mode, and the remote operator operates the arm to hand over the drink, welcome drink to the spectators. We also develop another two services. One is a photography service, and the other is trash collection service. As for the photography service, HSR, which is the subject, and the photographer HSR, which gripper is changed to the camera, moved to the seat in a row. The subject HSR is operated by a remote operator, and the photographer HSR take a picture while moving automatically, according to the instruction of the remote operators. As for the trash collection, HSR and the trash collection robot DSR move to their seat in a row. When the remote operator moves HSR sideways, the trash collection robot DSR automatically moves to the place where the HSR was and approaches the spectator's seat. This is the road services we provided. In fact, because the Tokyo 2020 games were held without spectators due to the pandemic, we were not able to provide the service to the wheelchair spectators. Instead, we provide the services to the volunteers, press persons, and the competition person in the stadium. Before we started this service, we were concerned how well this service would be accepted. Word of mouth about this service spread among the stadium staff, and we were able to provide more than 3,200 services during the 9 days of the track and field competition. Here's some comments from our remote operators. I feel my world has expanded. I would like to bring this experience of diving into the unknown world through HSR to people with more severe disabilities. We believe that the remote operator offers the possibility of providing a service using HSR. I explained the system concept and explain how autonomy and manual control are combined in this system. Actions such as a long distance move or routine actions are performed automatically. Actions such as changing the height of the handle depending on the spectators are performed by a manual operation. When moving by manual operation, obstacle avoidance is automatically activated and overrides the command, allowing the operators to operate the movement without contact with any spectators. And here is a configuration of the remote operator's interface. The remote operator checks the situation on the site by viewing the real-time camera from the robot and 3D view images on the operating screen. The 3D view image displays the autonomous movement path, camera view path, camera view angle, and obstacle information detected by the laser sensor. Here are some problems we encountered in this robot service. As for the remote control, the remote operator needed to practice to some extent to become used to this operation. Another issue was the slow and careful operation of the arm was required to prevent it from contact with the spectators. In order to solve these issues, we are developing an interface that easily and intuitively conveys the person's intentions, as well as the technologies necessary to achieve the both safe and fast operation. Here is some technologies we are developing now. As for the interface, we are developing a 2D hand drawing interface using a hand draw input with an electric pen. We are developing an interface that allows users to indicate the position for the grasping by drawing a symbol that represents the grippers. As for the technology required for the safe and fast operation, we were developing a low inertia and high back drivability arm with a wire-driven mechanism. This has already submitted in this IROS. Please check that paper. And we also developing an algorithm that fast and robust full body control algorithm. And we also started to consider the next platform for HSR. In the next platform, we think it would be good if the platform can contact more safely with the environment more than current HSR. We believe that research on gathering meaningful data by interacting with the environment is becoming more active. This is a draft idea for the next platform. So if you have any request, please let me know. I will be happy to hear your request for the next platform. That's my conclusion. We are promoting both continuous research and real-world applications. to realize our ultimate goal. As a real-world application, we introduced the robot service at Tokyo 2020. And the realization of human support robot requires the development of various technologies and their integrations. So we'll keep on co-creative research. Thank you for your kind attention.
Yeah, so we have coffee break from now. Please ask them if you have questions. And our coffee break is until 3:15. So please come back until 3:15. Thank you.